Okay, folks, Calc 3. So here's a cool thought for you. Calc 3 is Calc 1 all over again, but in 3 dimensions. That's right. We're going to do Calc 1 all over again. You're like, hey, cool. That's true. So the other good news that I think you'll be happy to hear is that we're not going to do sequences or series. Good news, right? I knew you'd be happy to hear that. That you do have to know how to integrate, like the stuff you learn in Calculus 2, like integration by parts. We still want you to know that. So that's going to be important. Don't worry. So I do want to just show you a quick thing about how Calc 3 is going to do Calc 1 stuff in 3D. So let's do some Calc 1 real quick here. Not a Calc 1 problem, just sort of an idea. One of the things that you learned in Calc 1, I'm hoping, is that if you had the graph of, say, y equals f of x here, and somebody said, hey, here's a point on the graph, I want you to give the equation of the tangent line to that graph. So there's the tangent line in pink. Now, does anybody remember when you were in Calc 1 how you got the slope of the tangent line?
Derivative.
Good. You got the derivative and you evaluated it at the x coordinate of the point that you were trying to find the tangent line to, that went through that point, right? So that's important. So you have to know how to do derivatives. Cool. So what's this got to do with Calc 3? Well, I just want you to know that in Calc 3, we're going to be working in 3 dimensions. You're going to have 3 axes, the x, y, and the z. And instead of a curve, you're going to be looking at this function of 2 variables, z is equal to fx comma y, which will graph as a surface. So I'll just draw like a capping surface here. This is a surface. And then somebody will go, hey, what if I'm on the surface? So what if I'm on a point right there? And instead of a tangent line, I'm going to draw a tangent plane. So if you can imagine this plane here, it's like a flat surface, is just kissing the surface at that one point. That's why they call this a tangent plane. And you're going to learn how to get the equation of that tangent plane, similar to you getting the equation of this tangent line over here in your Calculus 1 class. So you're going to learn how to do that. Pretty cool. So what's one other thing that you learned in Calc 1 that you'll be learning here in Calc 3? In Calc 1, another very important concept you learned was, again, let's say you're here in 2 dimensions and you were given some graph y equals f of x. Do you guys remember when your Calculus 1 teacher asked you to find the area under the curve between A and B? How did you do it?
Integrating.
Very good. Yeah. You had to integrate. Sure. You had to go, all right, the integral going from A to B, f of x dx. So what are we going to do in Calc 3 that's kind of like that? Well, back to 3 dimensions here. There's 3 dimensions. Let's do that surface, which is a function of 2 variables. Z equals fx comma y. Here's the graph. It looks kind of like a, I'll just do a capping surface. There's all kinds of surfaces there. And then underneath that surface, its projection, or the shadow it makes on the xy plane, will be the base of that solid. And here's what I'm asking you to imagine. Imagine that this is a solid where the top is the capping surface given by your equation there. And somebody said, go get the volume. How would you do that? Well, we're gonna do either a double integral or we're gonna do a triple integral. And it'll turn out to be really fun. Don't worry. So we're gonna do something called multiple integration here in Calculus 3. Aren't you excited?
Very.
Very, you should be really excited, yeah. So the other diagram I wanted to show you is here in Calculus 3, there's basically going to be 5 modules of material, 5 modules. The first module we're going to do is going to involve no calculus at all. So the first 2 weeks of class, I'm not going to cover any calculus. What? So when you go home and your mom goes, hey, honey, how was calculus today? You could go, oh, we didn't cover any calculus, Mom. And she'll go, what am I paying good money for? You go, Mom, we have to cover vectors first to lay a foundation so that we can do the calculus. And that's what we're going to do. After we get done laying the foundation doing vectors, the next big module, you're going to use your vector knowledge and learn a new kind of function called vector valued functions. And we'll have fun and play with vector valued functions. Those are fancy curves. After we get done with vector valued functions, we're going to learn another kind of function, functions of more than one variable. And that's where the surfaces come into play. And this is where you're going to learn how to do what's called partial derivatives. And then after that, the next module is where we do multiple integration. That's the double and triple integrals. Now, when you guys go to your four-year institution and you take a thermodynamics class, in thermodynamics, they actually like you to do 6 integrals at the same time. I'm not making this up. I'll show you something that is from a thermodynamics class. These 2 modules put together are known as multivariable calculus. So those 2 modules together. And then the very last module of the entire class, and this is where you're going to feel like the Olympic athlete going for the gold, is vector calculus. And we're going to use all of the previous modules just for us to be even able to understand vector calculus. Don't worry about it now, but that's how we'll wrap up the semester. Okay? So this is the semester and this is how it's going to go. And we're going to start here at the vectors. So hopefully you guys are ready to go because I'm ready. Let's do 2 dimensions first before we jack up into the 3 dimensions. So we'll start off easy, 2 dimensions. So we're going to learn about vectors in 2 dimensions. And the word in the plane is not going to mean a jet plane. From now on, anytime you see the word plane, it means 2 dimensions, 2D for short. Okay, let's do some definitions and get some basics out of the way. I hope you're ready. Let's go for it. So what is a scalar quantity? Well, you know, a scalar. So anytime I go, hey, folks, what's a scalar? You're going to go, oh, I know what that is. So I'm going to write this down, and hopefully on your course reader that you got already, or if not, you're going to get it today at the bookstore. You're going to write down, it's simply a single real number. So scalar quantities are physical quantities that can be characterized by a single real number. What are some examples of that? Some examples are length. Length is a scalar. Area is a scalar. Volume is a scalar. Vector quantities. Now, what's a vector quantity? Now, this is different from a scalar quantity, so know the distinction. These are 2 very different things. A vector quantity is a quantity that involves both a magnitude and a direction. What the heck is a magnitude? A magnitude is a fancy word for length. Well, why don't you just say length instead? Because magnitude is more universal. Because when you get into 4 dimensions or 5 dimensions, which we're not going to get into in this course, but if you are taking linear algebra, you will get into 4, 5, 6, 7, 8 dimensions. They still can talk about magnitude, but you can't picture a length. But so they use the word magnitude. Okay. Direction just means where is it pointed. Some examples of vector quantities are force, velocity, acceleration. If you've already taken a physics class, then you know these. If not, I'm glad, because I always try to coach my students to take calculus 3 before they take their physics. Students who take calculus 3 before they take physics tend to do better in their physics because they've already covered all the stuff like vectors and they need to know in massive detail. Okay, now let's talk about vectors and what they look like, folks. So if you've never dealt with a vector before, welcome. I want to start you from scratch so that you really get it. So don't worry. Here we go. A directed line segment, write that down, directed line segment is used to represent a vector. That's all a vector is. That's a fancy phrase for an arrow, people. A directed line segment is an arrow. Yeah, here's a picture of a vector. It's an arrow. Yeah, I know. And that's what a vector looks like. Isn't that cool? So I want you to get, though, a vector has 2 points here, point A and point B. So point A is known as the initial point. Write this down because this is super important vocabulary, which is also known as the tail of the vector. The point where the arrow is located is called the terminal point. That's the point B in this picture. And it is also known as the tip. So vector just is an arrow, people. Let's talk about notation, because on your handwritten work, you need to follow all of the rules and regulations for the symbolism of math. Notation is important, and I got you points unless you don't follow it. So what about denoting a vector? Well, this vector that I have here with AB as initial point and terminal point in that order is just AB with an arrow over the top, like a hat. Notice that order matters. The vector AB is different from the vector BA. Well, what would the vector BA look like? It would look like this. I'm sketching it for you. BA would have the same length as AB, but it would be pointing in the exact opposite direction, where A is the terminal point instead. Okay, when you're reading the book or you're taking a MyLab Math test or doing homework in MyLab Math, you're going to notice they don't usually use the notation for vectors with a little arrow on top. That's because in textbooks they use boldface. So if you see boldface, that means it's a vector. Now, when you're handwriting, though, you don't do boldface. You would write V. I usually don't put the full arrow. I'll just put the V like this. And so when you're handwriting, put a V with a little arrow on top. Okay, that's a little hat. Key weird fact. This is the key weird fact. Every vector that you see, an arrow essentially, actually represents a whole family of vectors, a whole set of vectors, each having the same magnitude, that's the length, and the same direction. So when you see like this vector here, AB, that represents every single vector in the world. Like I could draw another vector over here, that there's AB all over again. Here's another AB. All the millions of vectors that look exactly like that have the same length and are pointed a little bit upward and to the right. That's important that you get that sort of infinity representation. Now let's talk about standard position. What the heck is standard position? When you see a vector in standard position, it means that it is having its initial point located at the origin. And we're going to draw pictures in a minute, don't worry. Now let's do another definition. Component form. This is key. The component form of a vector in a plane, when your vector is in standard position, is written like this. You have your boldface here, V equals, and then you have angular brackets, and then a number, comma, a number. The V1 and V2 represent scalar components of the vector. So they're just pure real numbers. So we're going to use a component form for the rest of the semester, and you're going to use it too when you write down vectors on your handwritten work. Okay, now our physics brethren use a different way to represent a vector, but I don't want to get into that yet. In fact, we might not get into it till Wednesday. Depends on how much time I have today. See how far I get. but for now, component form. Now, what about the zero vector? What the heck is the zero vector? The zero vector is denoted with a 0 and a little arrow on top. That's not to be confused with the number 0. The number 0 is different from the vector 0. And in component form, it would be angular brackets 0, 0. And when you graph it, it just looks like a dot because it doesn't have any real direction. They say it points in all directions. We'll get to that picture in a minute. I got to lay down some more foundation here. I know I'm going kind of fast and giving you all sorts of stuff, and you'll hopefully watch the lecture later after I posted it. Let's talk about magnitude now. Magnitude, remember, is a fancy word for length. It's the length of a vector. So how do you get the length? Here's the good news. If somebody gives you component form, you can easily find that length, the magnitude. And here's the formula and the notation. I like to denote my magnitudes with double vertical bars. Unfortunately, your book, Briggs, only uses single bars. If you want to warm my heart, I'm not going to mark you wrong if you use the single bars, but it will warm my heart if you do the double bars, because other textbooks use the double bars when they're representing magnitude of a vector. I shy away from the single bars because the single bars kind of looks like absolute value, and we're not taking the absolute value of the vector. In fact, don't even say that. Don't go absolute value of a vector. I'll go, And a couple more formulas, and then we're going to do a big old example that will use all this info that we just went over. So let's say somebody gives you a point. Now, points in this class, you use parentheses, and vectors, you use angular brackets. Know the difference here. So let's say you have a point P with coordinates x1, y1, and you have a point Q with coordinates x2, y2. So let's say P is here, and let's say Q is over here. And let's say you want to form the vector PQ like this. Here's the vector PQ. How would you do this so that you can move your vector or translate it over into standard position? In other words, force P to be located at the origin, move him. Hey, come over here. And then Q will move along with you just so long as you maintain the integrity of the vector where it's still pointing in the same direction, it has the same length. So the magical formulas are here. The new X for your vector, the new X in standard position, take the difference of the X coordinates of the 2 points, but order matters. It has to be terminal minus initial. So P would be the initial point and Q would be the terminal point. And you want to do the terminal X coordinate minus the initial X coordinate. That will give you the brand new X coordinate of the vector in standard position. And then similarly for the new Y coordinate, take the difference of the Y coordinates. Okay, now let's do an actual example. And hopefully everything we've just discussed in the last 15 minutes will start connecting for you. Here we go. The point A with coordinates 8, -3. While I'm here, let me just graph the point A. There it is. And then the point B with coordinates 4, 5. It's going to be right about here. There he is. And we're going to create the vector AB. Remember, not BA, AB. Now this vector is sort of just hanging out there. It's not in standard position. How do I know it's not in standard position? I'll stop here. Anybody want to try that one? You can type it in the chat too if you feel bold.
It's not located at the origin.
Right. Yeah, your initial point is not situated at the origin. So this vector, even, by the way, it's okay not to be in standard position. It's just harder to do business with vectors that aren't in standard position, so I don't like them. But it's known as a geometric vector. Vectors that are not in standard position are known as geometric vectors. Okay, so what our goal is we'd like this vector to be translated or moved, if you will, so that we lift it up and stick it where A does end up being right here at the origin, and then B will be kind of more like somewhere over here, so it's still going to point in the same general direction. So the question is, we know that we want the A to get moved over here to the 0, 0. That's by definition standard position. But where exactly is the B going to get mapped to? And that's where these two formulas come in handy. Okay, so when we're forming this vector AB, the new X coordinate is going to be the terminal point. So you're going to go 4, that's the X coordinate of the B, minus the X coordinate of A. So -4 will be the new X coordinate. And the new Y coordinate, terminal minus initial here, will be the terminal point B's Y coordinate, which is 5, minus the Y coordinate of the initial point, -3. But 5 minus a -3 is 8. So what we're saying here is that AB is going to be the vector, use angular brackets here now, this is important, with -4 and 8 as its scalar components. The two pure numbers here, because a scalar is simply a pure number, are -4 and 8. So if I find -4 and then 8, where is it here? It's right about here. There's the coordinates -4, 8. The new vector, which is really the same vector as AB, it's just translated over here into standard position now. See? And that's known as an algebraic vector, one that's in standard position. Yay! So the answer to letter A here is -4, 8. We already did letter C. We did the new sketch of both the geometric, there's the geometric vector out here, and the algebraic vector, but we haven't done letter B yet. So we're doing this a little out of order. Don't worry, that's okay. They want us to find the magnitude. That's what those double bars mean. So the magnitude of the vector AB is going to be the square root of the sum of the squares of its scalar components. So what's that going to be? What the heck is 16 plus 64? It's square root of 80, which is actually the right answer, but I'll take away 1 point if you leave it like that. I don't want you to convert to decimal. I want you to simplify your radicals. So it turns out that if you factor 80, the largest perfect square that's a factor of 80 is 16, and then the square root of 16 is 4. So the final answer that I want to see as the magnitude, the length for this vector is 4 square root of 5. So that's the answer to part B. Yay! And we're done with this example. I want to mention that this magnitude here, if it feels like it looks like a distance formula, it actually is. It's the distance between this point, -4, 8, and the point 0, 0. And you learned how to find the distance between 2 points, probably in a pre-calc class, maybe. So it's just using the distance. Equality of vectors. This is super key. Put stars by it. It looks really basic and almost like it's a no-brainer. Like, of course that's true. How could that not be true? But it's going to come and save us for later. So suppose you had a vector U, and of course they're using that component notation with the angular brackets and their scalar components U1, U2, and you had another vector V with components V1, V2. You can say they're equal if and only if the scalar components match. So you need U1 to exactly be the same number as V1, and you need U2 to be the exact same number as V2. And you might go, well, duh, you know, for example, the vector 2, -3, let's say there's U, would be exactly equal to the vector V, 2, -3, right? Well, yeah, of course. And that's why I'm saying you're probably thinking that this is not a very smart definition, but you'll see where it's going to save us. It's a simple concept and necessary. Now let's do some vector operation stuff. Okay, folks, fill in the blanks. Suppose you got two vectors u and v and they're vectors in the plane. What does the word plane mean again? Not jet plane, but what?
2D.
2D. Yay. And c is a scalar. That just means c is some real number. Your favorite real number. I don't know. Yeah. The vector sum, and you're going to want to add two vectors together, people, u plus v. And it would, in slow motion, if we're doing the intermediate step, it would be this vector here, that component form plus the other vector. It's going to be a vector. So put in the angular brackets. The x component, that would be the first one, is going to simply be the sum of the x components of the vectors u and v, and then comma, that's a comma, and then the y component will be the sum of the y components for those two guys. Yeah, that was easy. Okay. Yeah, looks easy. What's a scalar multiple of a vector? It looks like this, and then the intermediate step would be that. And what you're going to do is you're going to distribute that pure number over the brackets, and you'll have new scalar components. And then you'll get the vector is just going to be either stretched or shrunk. How do you do the opposite of a vector? Well, you negate the vector, and negative is just like multiplying by -1, same thing. And you'll get a vector with components negative v1 and negative v2. What if you take the difference of two vectors? Can you subtract two vectors? Absolutely. Why not? So how do you subtract two vectors? Well, it's similar to addition. You're going to get a vector. So put your angular brackets in there. And the x component will simply be the difference of the x components of those two vectors, that the operand vectors, comma, and then the y component will be the difference of the y's. And we're done with that. So there's your operations. Seems matter of fact, straightforward. Sure. Let's do a visual on this. I'm going to show you two ways to think of adding two vectors, and they both end up with the same result. They're just two different perspectives of adding. So, but I want you to know both because I want you to be smart Calculus 3 students. Okay, tail to tip. This is also known as the triangle method. Okay, and I'll show you a little animation here in a moment of why it's called the triangle method. Okay, suppose you had a vector u, there's u, and some other vector v over here, you know, way over there. How would you add these two guys together? If you're going to use the triangle method, what you do is you translate the v vector. So I'm just going to copy down the u vector, and I'm going to move the v vector so that he's still pointing in the same direction and he's still maintaining his same length, but I want his tail to be sitting on top of the tip of u. Now, here's why they call it the triangle method. I hope you can see. You're going to connect the tail of u to the tip of v and get a new vector, and that's the sum. And you're done. You just are giving a picture of what the sum of u and v look like, and that is called the resultant vector. Now, what if you did this using what's called the parallelogram law, which is what much more commonplace, especially like if you go take a physics class. So again, let's say you had a vector u, same u, and let's say again, v is out here, and you want to use the parallelogram law to visualize u plus v. So you're still going to do a translation here. I'm going to, again, not move the u, so I'll just copy down u, there he is. And I'm going to translate v so that his tail is touching u's tail. He has to maintain the same direction and magnitude. Now, here's why they call it the parallelogram law. Can you imagine that these two vectors are adjacent side lengths to a parallelogram? Sure you can. In fact, with dotted lines, I'll just sketch in what the other two sides would look like. And now, draw the diagonal for that parallelogram. That diagonal is the vector u plus v. And notice it looks the same as the first method we did. That's because you want it to be the same. Same thing. That's just called the parallelogram law. So I wanted to show you this little animation here for, oh, not that. I screwed up. Not projections. Not that. Damn it. So here's what it looks like when you're adding vectors using that triangle method. I can move around that point, and the red vector is the sum of the two pink vectors. Yeah, woo, whoa, that looks pretty. And then if you're using the parallelogram law, so the two pink vectors, you're adding those two pink vectors together, and then the parallelogram diagonal is the sum there. I don't know if I can move anything here. So if I move like one of these guys down a little bit, you can see that that diagonal, the magnitude of it changes a little bit. I wonder if I can move it down here. Woo, yeah, still, yeah. So you can see the red vector is the resultant vector. It's the sum. Pretty cool, huh? You should be duly impressed. What about vector subtraction? What can you do there? Well, you can use either the triangle method or the parallelogram law, and then you can use the opposite of a vector. So once again, suppose you have the vector u, there he is, and a vector v. So one way you can do it, and this is the way I like to do it, is I like to do the triangle method in that you're going to make a triangle, but it's going to, the u minus v is going to connect the two tips. And u minus v, his arrow ends up at the tip of u. If you were doing v minus u, so here's u again, and here's v. What if somebody says, well, I want v minus u instead? Fine. You're still going to create the triangle here. This right here is v minus u. Okay. So if you want to know, well, how do you do that? How did you figure that out? Like if I use, here's u, and then I draw the opposite of v, which is just pointing in the opposite direction, like that. That's negative v. And then I sum these two up using the parallelogram law. So if you can imagine these two vectors adjacent side lengths of a parallelogram, then the diagonal there, that's u plus negative v, which is the same as u minus v. So you can see that this vector I have in red here is essentially, well, it should be the same length as that vector there, but I drew my u a little bit longer. That didn't look so good. And there's basically vector subtraction. Now, what about scalar multiplication? What does that look like visually? Let's check it out. So what does scalar multiplication do to a vector? We already saw how to do it analytically up here in the operations box. We saw that when you're doing scalar multiplication, you just take that pure real number, the scalar, and distribute it. So what? But what does it visually look like? What are you doing to the vector when you do that? So I'll show you an example. So here we are, x and y axes. Let's say you had a vector. I'm just going to draw some old vector in standard position. I don't know, v. If somebody said, I want 2v, what would that look like? That's a scalar multiple of the vector. It would just double the length of v. It would still point in the same direction. It would just be twice the length. There's 2v. What if somebody said, I want to go in the opposite direction? I want negative 2v. Okay, you're going to go in the opposite direction and then also double the length. So that would look like, well, that's not looking too good, negative 2v. You can even do fractions. What if somebody said, well, I want 1/2 the vector v. So you would go about halfway up, halfway in length, still pointing in the same direction. And that would be the scalar multiple 1/2 v, what it would look like in standard position. Okay, and that's scalar multiplication. You're either stretching or shrinking a vector. Pretty good, pretty easy, nothing fancy. If you've already done a lot of work with vectors before, and this is really review for you, okay, that's good too. I'm going to put you in breakout rooms right now, and you and your buddy are going to come up with what 2/3 u is, v minus u, and 2u plus v. For all three of these, you and your buddy, the answer better involve angular brackets, and then a number, comma, a number inside the angular brackets. I'm giving you a hint as to what your final answer must look like for all three of these in example 2. Now keep in mind, you're given what u is. There's the component form of u. And you're given the component form of v. Use the given vectors u and v to get parts A, B, and C. So you and a buddy will do this now. Okay, let's resume. Sorry. Come on, baby. Yeah, there we go. Share screen. All right, so you're going to do 2/3 scalar multiple of the vector u. So you'll distribute the 2/3, and so 2/3 times -3 will be the first component, and 2/3 times -8 is the second component. Well, then what's that? I always like you to reduce your fractions to lowest terms to get full credit. So here the 3's turn into 1's, and you should get -2 as the first component. And then here, oh dear, -16/3 is the second component. And there's your final answer with the angular brackets, component form. Everybody get that?
Yes.
No? Okay. V minus u. So you're going to take the vector 825 minus the vector with components -3, -8. And it's just like we said, you're going to take, when you're doing subtraction, you're just going to subtract those components. And here you're going to go 25 minus a -8. You've got to be careful. There's a lot of minuses floating around. That's when I usually make those silly mistakes. How about you? Okay, 8 minus -3, I think that's 8 plus 3, 11. 25 minus a -8 is really 25 plus 8, 33. Final answer, angular brackets 11, comma 33. That's the answer for part B. And then 2u plus 5v. So this involves scalar multiplication and vector addition in the same problem. So you want to do the scalar multiplication first. It's kind of like PEMDAS in your algebra class. So when you do the 2, you're going to end up with -6, -16. And then when you do the scalar multiple with the 5, you'll have 40 and 125. And then you're going to add those two vectors together. So -6 plus 40 is 34. And -16 plus 125 is 109. Final answer, the vector with components 34 and 109. Everybody get that?
Yes.
Okay. Any questions so far? Now I'm going to do a hard problem. And yes, this problem is going to be on a quiz. So don't ask me after it's over like, oh, that's not going to be on the quiz, is it? I'm like, yeah, it is. It's not that bad. And if you're taking Math 254, or you've already taken it, this you'll know they do all the time in that class. What are we doing? You're taking a given vector and you're trying to rewrite it as a linear combination of a couple of other vectors. Well, what the heck does that mean? It means you're trying to find a couple of scalars, A and B, such that W can be written as A, some weird number, times that first vector U, which was given to us, plus some weird number B multiplied by the vector V, which is also given to us. So what you want to do to help yourself with this is do it in slow motion so it'll make sense. So here's what we're trying to say. We want W to be some number A, that's the unknown, we got to go get that, times the -3, -8 vector, plus B times the V vector, which has components 8, 25. And in W we know also, because they gave it to us, And then I'm going to do the scalar multiplication thing, which I distribute the A. So the new components for that first vector are negative 3A, negative AA. And then I'm going to do the scalar multiple with B. So I'll get a vector with 8B, 25B as components. And then on the right-hand side, you're adding two vectors together. And you guys know how to add two vectors together. We went over this and you just did it. You're going to get a big old vector. And you're going to add the X components together to get a new X component. I know it looks weird. And then you're going to add the Y components together to get the new Y component. Okay, now here is the part where you look at what you have so far. You have a vector on the left-hand side. And you have a vector on the right-hand side. And they have to be equal. What did we say about equality of vectors, people? Go back, go back, go back. Remember this? I told you this is going to save us. It's going to save us right now. What do you mean? I don't get it. I'm going to go over what I mean. If that left-hand side of the equal sign has to equal the right-hand side, you need the 14 to be equal to the X component of the right-hand side. And we need the 41 to be equal to the Y component of the right-hand side. Now, folks, this is a linear system of equations. And you learned in your beginner algebra class how to solve a linear system with two equations and two unknowns. Do you remember that at all? Yes, no, maybe?
Substitution. Isn't there a few methods?
Is one way to go, sure. I'm not going to do substitution. What I'm going to do is I'm going to rewrite the two equations where the unknowns are on the left-hand side, just because that's more traditional. And then I'm going to try to add the two equations together. Not yet. How about if I multiply equation 1 on both sides by -8? And how about if I multiply both sides of equation 2 by +3? Get a calculator because I'm probably going to screw this up. So I'm going to distribute. So what do I have there? I have 24A plus -64B is equal to 8 times -14, which is -112. And then when I distribute this 3, I'm going to have -24A plus 75B is equal to 123. Is that right? Let's add these two equations together. I eliminate the A, and -64 plus 75 is 11B, and that's equal to -112 plus 120. It's 11. Divide both sides by 11. B is equal to 1. Now, how do I get the A?
Sub into one of the equations.
Plug it into either one of the two equations, right? And I'll let you do that. And I promise you, if you do it correctly, you should get A is -2. What does that mean? It means that your W vector is able to be rewritten as the -2 times the first vector U plus 1 times the vector V. And that's known as a linear combination. We'll get more into that on Wednesday. I'm going to keep going. So I'm going to go till 11:40 today. If you have to leave early, that's fine. But I just want to let you know I'm going to go a little overtime just because I can. So you spend a lot of time going over the syllabus. Let's do properties. It's a theorem of vectors. Let's fill in the blanks. Suppose you have 3 vectors, U, V, and W, in the plane, and C and D are some scalars. What if somebody said, hey, add U and V together? Fine. It's okay to add it in the opposite order. You'll still get the same result. Oh, that's good to know. What if you have 3 vectors you're adding together and you first want to associate the U and V together? That's fine. Go do it. You'll get a nice answer. If you prefer you could associate and first add V and W together and then add U, and you'll get the same answer. How about U plus the 0 vector? Now, folks, remember we talked about how to graph vectors. You know, like if once you are given the component form, you simply find the point, draw an arrow to it. What does the 0 vector look like? It's just a dot. So anytime you add the 0 vector to any vector, and this is known as the additive identity, you're just going to get the vector, U. What if you add a vector to its opposite? You'll get the 0 vector. And make sure when you're denoting the 0 vector, you put an arrow on top. Otherwise, I think you just mean the number 0 and I'll mark you wrong. What if you have two scalars that you're multiplying a vector with? Go do it. You can either do it the way they showed you there by first multiplying D, then the C, or you could multiply C and D together first and then multiply it with the U. That's fine. What if you have two scalars that you're summing together and you multiply that with the U? Do it like that, or you are legally allowed to use distribution. Similarly, if you have two vectors that are getting multiplied by a scalar, you can use distribution also. 1 times any vector is the vector, and 0 times any vector is the 0 vector. And we're done filling in the theorem. Let's do lengths. We already talked about length. That's called magnitude. Suppose somebody asked you to find the magnitude of a scalar multiple. Well, you could just go do it the way we taught you how to do it. You know, the magnitude of a vector, remember, is if the vector is given to you with components, is simply the square root of the sum of the components squared. The sum of the squares of the components. What if you want to do this quick? Well, if you don't feel like doing it because the numbers are large, you could first just take the absolute value of the scalar and multiply it with V. This is true. Now we're going to talk about something super important for the rest of the semester. And I mean super important. Put super important here in your course reader. Right here, this theorem. Like this skill is going to be on pretty much every single midterm and the final. There you go. I've already told you something that's going to be on the final. Isn't this great? If you're given a non-zero vector, then this vector, which is formed by taking the original vector and dividing it by a scalar, the scalar happens to be the length, will give you a brand new vector. It'll be the first scalar component minus or divided by the scalar, and then the second scalar component divided by the scalar, which is the magnitude. That will be called a unit vector. And why is it a unit of vector? A unit vector is defined as a vector that has a magnitude length of 1. And it points in the same direction as your original vector. All right. When you do this to a vector, basically multiply it by the 1 over the magnitude or the reciprocal of the magnitude there. This is known as normalizing the vector. I am going to call it unitizing the vector because that's what you're doing. You're unitizing it. You're making it a length of 1. So I'm going to do an example here. And this example is similar to what's going to be on Sunday's quiz. So, and I'm going to show you what the pitfalls are too in doing this example. So pay attention so you don't fall into the pitfalls. So letter A is easy. They want you to find a unit vector, that means a magnitude of 1, that points in the same direction as the given vector. Okay, let's sketch the vector first, even though they didn't tell us to, because I want you to notice something, and you'll learn something too. So here's the X and Y coordinates. Let's graph this. Even though they didn't ask us to, I want you to see this. How do you graph this vector 3, negative 1? Like, show me. It's in standard position, yeah, but how do you graph it? You first find the point 3, negative 1. So there's the point 3, -1 right there. And then you draw a vector where the initial point is the origin up into that point. There's the vector. There's the vector v right there. Ta-da! I just drew the vector. And now we're going to unitize it. What that means is we're going to come up with a vector u that's pointing in the same direction as v, but has a magnitude or length of 1. And the way you do that is you use this handy formula right there. So that handy formula happens to need the magnitude. So let's go get the magnitude first. And I'm purposely not taking -1 squared because we all know that -1, when you square it, gives the same as +1 squared. So square root of 10 is the magnitude for this vector v, which is a little bit over 3. So it's a vector that's got a length of 3 point something. So the u is simply going to be the vector v divided by this magnitude. And I like you to distribute your scalar to get full credit. So your final answer to part A is this. Now, I know somebody's going to ask me, so I'm going to ask myself, do you need to rationalize your denominators in this course? No, I never require it. If you want to, go ahead, but I'm okay with square root of 10 being in the denominator for the rest of the semester. Yeah, it's okay. Well, I don't like it. My other teacher told me it's not okay. Well, okay, fine. If you want to go rationalize it, MyLab Math will still give you full credit and I'll still give you full credit. But you're wasting valuable time when you could be moving on to the next problem. So why would you do that to yourself? Just leave it. Now, how do you do letter B? How do you find a unit vector that points in the opposite direction of V? You're just going to take the opposite of U, which is the opposite of this vector we just got from part A. And then I'm going to distribute the negative, and that just means you're just going to change the sign of the component. Super easy. Your final answer for part B is the vector, so use angular brackets, -3 over square root of 10, 1 over square root of 10, and you're done. That's going to be a unit vector pointing in the opposite direction of V. Fine. Letter C. And I'm going to read both C and D because they're going to sound like I'm asking you for the same thing. And that's what the pitfall is going to be. If you don't get the difference, you're going to blow it and lose a lot of points. So listen carefully because they're asking for 2 completely different animals here. Letter C, here's what letter C is asking for. They're asking us to find a vector that points in the same direction as V, but has a magnitude, that's length, that's 8 times more than V. Okay, now I'm going to read you letter D. Letter D is different. Different answer. Find a vector that points in the same direction as V, whose magnitude is 8. Can you hear the difference? I hope so. In letter C, they're asking you to find a vector that has a magnitude 8 times more than V. So you're simply going to need to find 8V. So you're just going to take the original vector that has components 3, -1, and multiply it by this scalar, 8. Don't forget to distribute. So your final answer for letter C will be this vector with components 24 and -8. And that's guaranteed to give you a vector that's like 8 times bigger than V. If I had to draw it, it'd be like huge, pointing in the same direction as V. I don't have enough room. Now, letter D, they're wanting you to find a vector that's pointing in the same direction as V, but whose magnitude, whose length is 8. That's different from 8 times more than the V. So this is a 2-step problem. First, unitize V, shrink it down so it's a unit vector. But we already did this when we did part A. Remember, we got this vector here, this unit vector. Once you have your unit vector in hand, then you multiply him by 8. And this is guaranteed to give you a vector whose magnitude is exactly 8. So don't forget to distribute your scalar there, and your final answer is going to be the vector whose components are 24 over square root of 10 and negative 8 over square root of 10. Okay? I'm going to just do the last thing, the last theorem here, and then we'll call it a day. Okay? The triangle inequality. What the heck is that? Super important idea. You already looked at how to add vectors using the triangle method. If I go back to, where is it? When we were doing this, remember adding vector using the triangle method? Come on, baby. There's the triangle method. So the triangle inequality has to do with this right here. So I hope you can see that the vector, the red vector there, that's the sum of the two pink vectors, that guy's magnitude is always going to be less than or equal to the sum of the other two magnitudes together. So let's go write this down. I'll finish this. This is the magnitude of u plus the magnitude of v. So they're saying the resultant vector, his overall length, is less than the sum of the other two guys. Now, does that make sense? Like, look here, you've got u, v, and then the sum of u and v, like that. So, like, let's say this is your house. Looks kind of like a funny house. And over here is the school, okay? This is the school. If you wanted to drive to school, what's the shorter way to drive? Would it be first go along u and then go to v? Or would it do the straight shot u plus v? I hope you answered the straight shot u plus v. That's the shorter way. And that's all the triangle inequality says, is that that length u plus v is going to be less than or equal to the sums of the two original vectors. Now, less than, I hope you see, makes sense. But how about equals? What if u and v are pointing in the same direction? Then u plus v is sitting right on top of u and v, and that's the one time where the magnitude of u plus v will be the same. And that's called a deformed triangle. Yeah, right there. That's when you'll have the equality. Okay, so there you have it. That is the theorem of the triangle inequality. And that's all we have time for today, folks. So I'm going to end the lecture there. Congratulations on your first day of Calculus 3.